All right, good morning. So here is our new unit, which is current and circuits. This is one of my favorite physics topics because it's pretty much like magic. And so we're going to be looking into circuits. And an example of a circuit is kind of this picture here. You have a battery, you have a positive and a negative end. We've all seen batteries. Here's an example of a rechargeable battery. We have a positive and a negative end. You can see different stats on it, but the main one that we're going to go with, it's kind of hard to see, 1.2 volts is this battery. So we're going to kind of go over what volts are, what amps are, and what resistance is. So battery, we all know, kind of contains electricity, or some form of electricity, or a potential electrical energy is what we call it. So we have a battery, and in the picture, if I take something like a copper wire, or some sort of wire that can move electrical charges, generally metals, we can make an electrical circuit. And what a circuit is essentially you connect it to the positive end and the negative end, and it'll move electrons from the positive. It's called conventional current when it's from the positive to the negative. So electrons are going to move across the wire to the negative end there. So that is what a circuit is. Okay, generally from some sort of voltage or from some sort of potential energy state, it will move electrons along a wire back to itself, essentially. But you need it to fully connect back to this end for it to work. So here's the picture. You have a switch, and essentially a switch is just a part in your wire that can open up and break the circuit so that it's no longer a closed circuit, but it opens up. And when it opens up, it's no longer a circuit. And then it goes through, and here we have a light bulb. And then so what it goes up into the light bulb, and then comes back down, and then it'll continue through a wire to the negative end. So when it's closed, when the switch is closed, it'll go through the circuit, and it'll keep going around, lighting up this light bulb. So that's what a circuit is. So what you need for a circuit is generally we talk about batteries. We're going to be talking about direct current circuits. So there's two types of circuits. There's a DC circuit and there's an AC circuit. This is direct current. And then there's another one called alternating current. We're not going to be really looking at alternating current at all. But what is alternating current? It's a current that kind of moves back and forth instead of going just one direction in the circuit. And an example of an alternating current is our house or our houses. So if you plug something into an outlet, that's an example of alternating current. Direct current is batteries. So when you connect stuff to batteries, that means that's a direct current. So examples are your calculator, or your video game controller, or your remote, anything where you plug batteries in, that's an example of direct current. And that's what we're going to be looking at. So let's go over the three main types of things with electricity. We have something called voltage, something called current, and something called resistance. Inside the brackets, you can see I have put the variables of each. So voltage uses the variable V, current uses the variable I, and resistance uses the variable R. Okay, kind of weird that current starts with a C but uses I. Kind of the main thing here, the reason why it doesn't use C is because a different variable uses that C, and it's charge. Charge uses the C's. But anyways, so what is voltage? Technically, it's the potential difference of energy per unit charge, and units volts, which is joules per coulomb. And what's a coulomb? A coulomb is a unit of charge. So it's how much charge something has, or how much extra electrons they have. Okay, so an example is an electron has a charge of 0.00000000160 coulombs. So you can see that a coulomb is a lot of charge, or a lot of electrons worth of charge. Okay. To be honest, this unit here is very technical, potential difference, or voltage. If you look into the definition, you'll be seeing this more in grade 12. So what you really need to know what voltage is, it's the pressure of a circuit. And the interesting thing is it uses variable volts, but also the unit you put after it is also a V, okay, for volts. So it's the pressure of a circuit. So if we look at this battery here, it has 9 volts of pressure that it can give to a wire if you connect it. Okay, so it has 9 volts of pressure, okay, which is quite a lot. If we look at our other one here, this one only has 1.2 volts of pressure it can give to a circuit. So if I connect one light bulb to this battery here, it'll light up. If I connect another, or the same light bulb, but to this battery, which has 9 volts, almost 9 times the amount of pressure as this one, it would light up way more because it has more pressure. Okay, so that is what volts are. Okay, now let's go to current. Current is the dangerous one, because we all know that electricity can be very dangerous if you don't know what you're doing. So current, the technical definition is change in charge per second, or the amount of charge per second. So when you connect your battery to this wire, electrons move really quickly through this wire, and a certain amount of charge is moving every second. Okay, you could tell if it moved faster, more charge would move, or if there was more charge moving at a certain spot. You can kind of think of it as the current of water through a pipe. Okay, so water current, how fast the charge is moving per second. And the unit they use is amps, which is an A. And what unit that is coulombs per second, which is coulomb per second. Coulomb is a unit of charge. So how much charge is you moving every second? If it's 1 coulomb per second, that's 1 amp. 1 amp of current. So to give you in reference, a few milliamps, if it reaches your heart, can kill a person. Okay, so a few milliamps, so let's say 0.02 amps in the heart is deadly. Okay, so you can tell that amps can be dangerous. Alright, so the next one, resistance. The ratio technically is called the ratio of electrical potential difference, V, to the current. Okay, its units are ohms. Okay, so its variable is R, its unit that you put afterwards is this weird omega symbol, which is called ohms. But overall, this box is more useful. Current is the speed of a circuit, how fast it's moving, and your resistance is the slow effect of the current. Okay, so if I were to connect just a wire straight to this battery, like so, it would get really hot really fast. And the reason why is because I don't have any resistance in this circuit. I wouldn't have put a resistor or a light bulb or anything in the circuit, so it would get really hot really fast because there'd be barely any resistance or any slow effect. So every circuit generally needs some sort of resistance to slow that current down. Alright, so let's go into the basics. How do we draw a circuit? We have a picture here. This is called a switch. You can picture it as just like a light switch. It's like this. It's an open switch when your light switch is turned off, okay, when there's no current going through it. Because when it's open, the wires are not touching, and so electricity is not flowing through. This one here is a closed switch. Okay, you can tell because it's touching. This would be when you flip the light switch on. Then it would be a closed switch because the wires are touching or are closed and electricity is flowing through. This is an example of a fuse. We won't be using that. Battery. Here's an example of a battery. These are called cells or dry cells. So a battery is a certain number of dry cells in a row. So if I wanted to draw this in a simple circuit diagram, I would instead draw that symbol there. And that's the same thing. We have voltmeter here. And what a voltmeter is it's a device that can measure the pressure of a circuit. Okay, so it can tell you directly how many volts are. So if I hook something up to this battery, or a voltmeter to this battery, when it has a circuit, it can tell me how many volts it's actually using. It says 1.2 volts, but it's rechargeable, and it might not be quite 1.2 volts. This one here is an ammeter, and you can see the A. So it measures current, A for the unit amps. So how much current is running through something, you can use an ammeter. So you can see how much current actually goes through something by measuring it. This one here, buzzer, we don't use. This one here is a light bulb. Generally I draw that symbol there for our light bulb, but you can draw either. And then another one here is a resistor. Okay, and again a resistor is shown as that squiggly line because it slows the current down. If you picture kind of a tube, if you kind of put lots of bends into it, it'll slow the current down. One thing to note is a lamp is an example of a resistor. Okay, so a lamp is really just a resistor that produces light. Okay, so anything that you put into a circuit is essentially some sort of resistor. All right, so how do we draw a circuit? If I'm going to draw my example here, I'm going to start off with the battery or the source. And usually I just draw 2 or 1 or something. I just need that symbol essentially. And then I start going around, and let's say we put a resistor in it. So I'll draw that, and it'll go around and it'll come back. You need a positive end and a negative end, which just means that this end likes to give away electrons, this one likes to have electrons. So essentially you go from the positive end to the negative end around like that. And that's called conventional current. You go positive to negative. But the one thing you have to remember is the positive charges are not moving. Really, the negative charges are moving, or the electrons are moving, but we go from positive to negative. This is a resistor, and the current's going that way. So it goes through the resistor, and then that way. All right, so that's an example of current. If I wanted to draw another one, sometimes I just draw one cell just to, because I'm lazy, and then I go through this way. Say I go through a resistor again, and I close off just like the last one. Direction's going that way. But say I branch it off, I could also make it go to, say, a light bulb. Now it's a light bulb there, a resistor. And say I want to test how much voltage this light bulb has. I can put a voltmeter on the end there. So now the current is going just like a river. It goes out and then it branches off, so it goes this way and this way, and then goes that way and that way. So it goes through all the branches and then comes back and all arrives here and then back to the battery. So that's an example of how to draw another circuit. All right, now here it says, can you draw a circuit through a switch, a lamp, and an ammeter? Okay, so I have a battery, positive, negative. So it says it wants to go through a switch. So I'm going to draw my switch. A lamp, which is a light bulb, and an ammeter. There's a circuit. It goes through all three, and that's what they asked for. So that's how I draw a simple circuit. One thing to note here is voltmeters are always drawn kind of out to the side. If I wanted to test the voltage of this battery, I would draw a voltmeter like so, kind of off to the side, where the current can either go through there or through the voltmeter. It has a choice. But when it comes to amps, or an ammeter, the other one which measures the speed of a circuit, you always have to put it straight in the circuit itself. You can't put it outside like that. You have to put it right in the circuit so that all the current has to go through the ammeter to measure it. Okay, so that's a side fact kind of to know. Alright, so let's go through some sample questions to see how these kind of work. So what are some typical current, voltage, and resistance numbers? Just so, because we're just learning these variables, so let's just look and see what some things in real life are. So we know that most batteries are in between 1.5 to 9 volts. Okay, so a D battery I think is 1.5 volts. You can see we have this 9-volt battery on the front. We have these ones, which is 1.2 volts. So the size of the battery doesn't actually quite tell you how many volts it has. The size of the battery pretty much tells you how long they'll last for, but won't tell you how strong their pressures are. An outlet at a typical household is either 120 volts or 240 volts. Generally it's 120 is what I've seen. But again, that's alternating current. We'll see some examples using that for direct current, but generally it's alternating current, which works differently than direct current, and we won't be looking into alternating current. Another one is car battery. That's direct current because it uses a big battery. That's 12.6 volts. So you can see it's more volts or more pressure than a typical battery. If we look at current values, if you have a lamp connected to, say, an outlet, it would feel around 0.8 volt amps of current going through it. Okay, so a typical light bulb has almost 1 amp going through it. So 1 amp is definitely enough to produce light. And its resistance value for that lamp is 144 ohms. So our resistance for a typical lamp is generally around 144 ohms. Okay. Maximum household circuit would be around 15 to 20 amps at one moment or one point in time. And again, that's a lot of amps, is 15 to 20 amps. And that would be all in one circuit if you had it from the same outlet. So if you've ever seen Christmas Vacation where they plug in 1 billion lights into the same outlet, that would be reaching this 15 to 20 amp range and essentially would end up breaking a circuit and turning itself off. Typical Christmas lights, you put 50 bulbs on one kind of string of lights and you connect it to an outlet. Essentially each bulb will get 2.5 volts of pressure each. And then overall, our Ohm's law is the amount of voltage, or is kind of the main point of this lesson, is the amount of voltage is what pushes the current through resistors. Or your Ohm's law is essentially this equation, V equals I times R. Or your voltage is your current times your resistance. Okay? And then this equation here is not Ohm's law, but it's your other main equation, which is your power. We've all heard of power, which is watts, is equal to your current times your voltage. So these are your two equations that you're going to be using to answer any questions to do with circuits. We all know power, so let's look at what we know about power. Power is work over change in time. Okay, so the amount of joules per second that is being used. Okay, since electricity can be seen as energy, it can also be seen as the amount of energy that's being produced per second. Okay, so the amount of energy that's produced per second is dependent on the current and the pressure of your circuit. Okay, So if you look at a typical device, say your fridge or your stove, you'll see how much power it kind of emits, or it can produce every second. Okay, generally the highest one I think was on a critical challenge, I'm not sure, but it's your water heater. Your water heater takes a lot of power because it needs to put tons of energy in per second to heat up water, as we know, because water has a huge specific heat capacity. But anyways, let's go into these circuit questions. A 6-volt battery delivers a 1/2 amp current to an electric motor. Again, everything can be seen just kind of as a resistor, if you want to simplify it, connected across its terminals. What is the power in the motor? If the motor runs for 5 minutes, how much electrical energy is delivered? All right, so we know if we want to, I always draw them first. It's going to go through some sort of resistor. I'm going to call this the motor. You know, positive to negative. So our 6-volt battery, I'll put there. And then overall our amps are 1/2. Okay, so we have the variable V, the variable I, and it wants to know the power of the motor. So let's use our equation. Power is I times V, which is 1/2 amp for I, and our voltage is 6 volts. So overall our power is 3. What unit do we use for power? We know power is watts. So 3 watts is essentially what this motor rating is, how much energy it produces per second. Okay, now it says if the motor runs for 5 minutes, how much electrical energy is delivered. When we know power is also work over change in time. So if we want to know how much work, that implies that work is power times change in time. I just multiplied by the change in time. And so our work is 3 watts times 5 minutes is 300 seconds. So my work is 900 joules. Okay, so if that motor runs for 5 minutes, it produces 900 joules of energy. It's not a very big motor. All right. Now let's look at the next one. So one thing I just wanted to add is if we wanted to, say, use Ohm's law for this last question, and I say I wanted to know how much resistance this resistor had, because it didn't ask us this, but I'm just curious. I'm going to use this, V equals IR. This implies that R is equal to V over I. And our volts is 6, and our current is going to be 1/2. That means this resistor has 12 ohms of resistance. Okay? So generally, for questions, if you decrease the resistance, it actually means more power. Okay, so the resistance kind of tells you how much power the thing will have. So this one has 12 ohms. If it had less, the power would be more. Okay. Now question 2. A car battery uses a current of 2 amps through a lamp and produces 12 volts across it. What is the power used by the lamp? So let's draw car battery to a lamp. Say the light of the car. We have 12 volts here, and this is going to be 2 amps going through this lamp. Okay, what's the power? Well, power is I times V from above, so power is going to be just 2 amps times 12 volts. And so our power is going to be 24, what unit? Watts. Generally, I write the word watts instead of putting a W because that can be confused with the variable work. So 24 watts is how much this light bulb kind of uses. We could calculate the R value just like last time, but it only wanted what the power was. Okay, question 3. A 12-volt battery is connected through an ammeter and a 3 ohm light bulb. What will the current be? So let's do a battery through an ammeter through our light bulb and then back. Alright, so this is 3 ohm. I always like to write the resistance beside it. And then this is 12 volts, the car battery. Alright, so we have those. The current's going to go that way around. So it wants to know what will the current be. So we have a resistance value and we have a volt value. So let's use Ohm's law. V equals I times R. So V equals I times R. This implies that R is equal to V over I. And so our volts is 12. And then our, do that back because we're not looking for R. So that's my mistake. We're looking for I. So we're solving for I. That means we have to divide by R. So I is V over R, which is 12 volts over 3 ohms, which will give us 4 amps. Okay, so the amount of current going through this whole circuit is 4 amps. And if you remember, ammeters have to go directly in the circuit so that it can actually measure that current. So it measures 4 amps, okay, if you were to put it in the circuit. And it would tell you that there's 4 amps in the circuit, in this circuit. If you were to increase and put more light bulbs in the circuit, it would actually decrease your current. But we have 4 amps. It says, what if the light bulb was 5? Well, we could do that. So if it was 5 ohms, then we can go current is V over R. This time our voltage is 12 and our resistance is 5. So if it had more resistance, then our amperage would actually go to 2.4 amps if I calculate that. Okay, so you can see that the amperage goes down as your resistance goes up. Okay, which makes sense because as you add more resistance in a river, the current is going to slow. So what it said, and now it says, what if there was no light bulb? So no light bulb. This is kind of a more theoretical one. If there was no light bulb and you just had your battery and connected a wire straight from your positive to your negative, theoretically we're going to use the same equation. I is V over R. What would our current be? Our voltage is 12. Our resistance we're going to say is 0, or one thing to note here is it would not actually be 0 because everything, even a copper wire, has some resistance. It'll have a very, very, very small resistance, but it'll have something. Okay, so let's just assume that it's 0 or no resistance. 12 divided by 0 is undefined. Okay, but let's say it was really small. 12 divided by, let's say, 0.0001. It would have 120,000 amps. Let's try a smaller number. 12.00000001 would have 12 billion amps. Let's say it was smaller than that. And we can see it just goes up. Okay, so if you actually get to that 0 point, you'll note that our amps keep going up. We'll get infinity amps. Okay, again, this is theoretical because everything has somewhat of a resistance, but if you connect a battery with no light bulb or no resistance, essentially your amps are going to go to infinity. What would really happen? So I'm just going to put danger. It would get really hot instantly because it has an infinite amount of amps and would essentially melt the wire and destroy the circuit in a split second. Okay, and if you were touching that, it would be instant death. But again, every current circuit has resistance. And one more thing to note is dry hands actually have a lot of resistance. Okay, so if I connect my hands to the circuit, I have, they would say, nearly 100,000 ohms of resistance through dry skin. But again, if your skin is wet, it reduces that, and if it's wet and salty, it reduces that even more. Okay, so again, electricity can be dangerous if you have very little resistance or a lot of amps. All right, so try the rest of the questions. Good luck. Thanks.